Welcome back, folks. In lesson 2.3, we're going to look at finding the derivatives of sine, cosine, exponential, and logarithmic functions. Okay, a bunch of different types of functions here. The one thing that's going to link this all together is basically we're just going to give you the derivative rule, show you how it works, and then look at mixing these different functions together, okay, to take derivatives of more complicated functions. All right, so here we go with that. We're going to start off by looking at the derivatives of the sine and cosine function. We'll say the derivative of the sine function, okay, so d over dx of sine of x is just equal to cosine x, and the derivative of the cosine function is a negative sine of x. All right, so derivative of sine is cosine, derivative of cosine is negative sine. Now I think intuitively that makes sense. Okay, if we think of those functions as kind of chasing each other up and down as they go, it makes sense that the slope of one of our functions is the same as the other one, and vice versa. Okay, how would we prove such a thing? Well, you do it like this. And I'm not going to do a full proof here, but we do the derivative d over dx of sine of x. What I'd do is I'd use my definition of a derivative. Okay, the limit as h goes to 0 of, in the case of sine of x, that would be sine of x plus h minus sine of x over h. Again, what I'd do is I'd use some trig identities, I'd rearrange this, I'd cross some things off, I'd evaluate it. Okay, eventually I'd end up with equals just the cosine of x. I'm not going to prove that for you here just to keep this video brief. If you ever want to go through one of these, we can do that before school, after school, if you're really interested. Otherwise, for this lesson, for the video at least, we're just going to give you the derivative rules and show you how to apply them. All right, so let's look at applying our derivatives of sine and cosine here. Okay, so problem 1, part A says let f of x equal 7 sine x minus 3 cosine x. And we want to use that to find f prime, okay, the derivative of f of x at x equals pi over 6. Okay, 2 steps. First thing we'll do is find f prime of x. Okay, so we have 7 times the derivative of sine of x. Now, a little scratch work on the side. We said d over dx of sine of x was just equal to cosine x. So that'll be a 7 cosine x. Okay, minus 3 times the derivative of cosine x, which we just said was equal to a negative sine of x. So I'm going to write that as negative sine x here. Now, obviously, you could combine the two of these in one step and make that positive, but if you're taking notes, it's good to leave some breadcrumbs as far as how you're doing things, all the different steps that you may not necessarily show when you're doing this on a test or a quiz. Okay, so I can rewrite then f prime of x as equal to just 7 cosine x minus, sorry, but not minus, we'll double the negative, plus 3 sine of x. All right, that's my derivative function then. You give me an x value, and I'll tell you what the slope, the instantaneous rate of change of my f of x is at that value, which we can do for pi over 6. Let's look at f prime of pi over 6 would be equal to 7 times the cosine of pi over 6 plus 3 times the sine of pi over 6. And then at this point, really what we have is just a trig problem. So we'll do a little trig scratch work on the side. Now you might be able to do some of this in your head. If not, okay, write it out. First off, pi over 6 is equal to 30 degrees, if we're thinking in terms of degrees. Pi radians is 180 degrees, so 180 divided by 6 is 30. Okay, so in this problem then, we're going to evaluate it using our 30, 60, 90 special right triangle with side lengths of 1 across from the 30, 2 across from the 90, and root 3 across from the 60. And for evaluating, we're using our SOH, CA, TOA. and we're dealing with 30-degree angle, so let's label that triangle accordingly. 1 is the opposite side of the 30. Root 3 is the adjacent side to the 30. And then 2 is the hypotenuse. All right, so evaluating then, f prime of pi over 6 would be equal to 7 times the cosine of pi over 6. Cosine is adjacent over hypotenuse, so that would be a root 3 over 2. And that's times. Okay, plus then 3 times the sine of pi over 6. Sine is opposite over hypotenuse, so 1 over 2. Which we can rewrite as we have a common denominator here, so I can just combine everything in my numerators. We could say 7 root 3 plus 3 all over 2. All right, I'm going to say that's my exact answer. That's the way this would show up on a multiple choice part of an AP exam. So this would be the exact answer. Now, we could run into this problem on the calculator portion of the exam, and it might just say approximate the solution. So we can't get the exact answer from our calculator, but here's what we can get. We can hit the math and scroll down to option 8 for a numerical derivative. We'll do that derivative with respect to x. You can use whatever variable we want, but let's keep it simple, go x. And then here we'll plug in the original function. Make sure you don't plug in the derivative. Okay, let's let the calculator do the derivative for us. So we can say 7 sine of x, make sure I close that parenthesis, minus 3 cosine x, close the parenthesis. And then we can scroll out into where we're evaluating that at. Well, that was just pi over 6. So we'll second pi divided by 6, hit enter. And that's going to give me a decimal approximation of this answer here. Now, maybe we're doing this on the calculator large portion. This is what the ABCD answers look like. How can I check and see if I'm doing this right? Well, if I plug this into my calculator, 7 square root 3 plus 3, all in the parentheses for my numerator, divided by 2, that gives me something that's pretty close to this approximation. Now, this is closer to my exact answer. Notice the answers are off as I get into the kind of further and further decimal places. That's because what the calculator is doing is it's not actually finding a derivative, it's approximating it. So it's okay if these only match up to 3 or 4 decimal places. We can still assume we got the right answer based on these results. Let's go ahead and run through one more of these guys together before we give you a chance to try one on your own. Same idea, we've got a function g of x equals 3x squared minus 4 sine x. We want to find g prime of pi over 4. Okay, now notice this one has some trig functions in it, as well as just a part of a polynomial, which we're going to apply our power rule to. So it's okay to combine those different rules based on our function. So here I'd say I have g prime of x is equal to applying my power rule. We'll multiply by 2 and then subtract 1 from the power. So that'd be a 6x to the 1. Now if you need to split that up into separate parts, feel free to do that, but we'll just keep moving here. Okay, minus 4 times the derivative of sine x we said was cosine x. And there we go, there's my derivative function. At this point, we can find g prime of pi over 4. It will be equal to 6 times the pi over 4 minus 4 times the cosine of pi over 4. And again, we'll do some trig scratch work on the side here. Pi over 4, 180 divided by 4 is 45 degrees. Okay, so this time we're talking about our 45, 45, 90 right triangle with side lengths of 1, 1, and root 2. Okay, we're talking so, ka, toa once again. We can pick one of our 45s. cosine is adjacent over hypotenuse. So then evaluating this then, we end up with, here I suppose I can reduce. 6 divided by 4 is 2/3. So we can say 3 pi over 2. 3/2. Yep, divided by 2, we get the 3/2. All right, minus then, we've got the 4 times the cosine of pi over 4. That'd be a 1 over root 2. All right, and if we want to plug this into the calculator and evaluate, we could stop here. Free response time, this is technically the right answer as well, so we could stop here. But AP multiple choice time, a lot of times what we'll do is we'll simplify, we'll rationalize the denominators, we'll combine stuff together. In this case, I can make this into a single fraction by rationalizing my denominator, multiplying by root 2 over root 2. Which will leave me with a 3 pi. And in this case, the root 2's will just turn into a 2. So I'll have a common denominator. So I can say 3 pi minus 4 root 2 all over 2 for this one for a final answer. All right, that's all the simpler I can make that. I can't combine or simplify anything else here. All right, part C is a similar question. Why don't you take a minute, pause the video, run through part C on your own, and then hit play to check your answer. Next thing we're going to do is look at the derivative rules for exponential and logarithmic functions. Okay, first off, for exponential functions, we'll say the derivative of a, the base, to the x is just a to the x times the natural log of a. And then a special case of that, when our base is e, the derivative of e to the x is just e to the x. Reason for that being is if I included the natural log of e, that's just a 1 here, so that part cancels out. And then also we have logarithms. The derivative of log base a of x is equal to 1 over x times ln a. And then the derivative of the natural log, okay, so log base e of x is equal to 1 over x. Okay, same idea. If we plugged in ln of e for our base, we'd get a 1. Okay, so 4 rules, but really it's just 2, where the e to the x and natural logs are just special cases of a to the x and log base a of x. All right, once again, where are these coming from? How would we prove them? Well, we'd look at the limit as h tends to 0 of each of these functions, reduce it down, okay, use some manipulation tricks. We'd be able to get to those. Okay, that's beyond the scope of this video, this lesson here, but if you ever want to see those done, feel free to swing in after class and we can check those out. All right, so let's go ahead and look at using those rules here quick. Okay, we'll run through a couple together and then give you a chance to try a few on your own. Okay, so once again, let f of x equal negative natural log of x plus x squared. We want to find f prime of e squared. All right, so coming up with our derivative function first, f prime of x is going to be equal to, I'm going to throw the negative out front first, and then remind myself what that natural log rule is. We said that d over dx of the natural log of x is just 1 over x. So here we have just a negative 1 over x plus, okay, then here we're back for our power rule, x squared. That derivative is going to be 2x to the 1. There's my derivative function. And then we can plug in the e squared to that, which we can say is equal to a negative 1 over e squared plus 2 times e squared. All right, and that's all the simpler I can make that, leaving it exact. Again, this is good for free response test. Multiple choice, the options might combine these into a single fraction. And the way I could do that is by creating a common denominator. Right now we have a 2 times e squared over 1. if we multiply that by e squared over e squared, we then have our common denominator. And we could write this as 2e to the fourth minus 1. Okay, or we could flip that order, but I'm just picturing multiple choice time, kind of them flipping it to make it look a little nicer. All over e squared. Okay, again, that's all the simpler we can make it, but that'd be what I'd predict happens, or they give you as an option for the multiple choice part of the AP exam. Let's go ahead and run through another one of these guys together. Same question, let g of x equals 2 to the x minus sine of x. We want to find g prime of 0. All right, so g prime of x then will be equal to the derivative of 2 to the x. Now a minute ago we just said that d over dx of a to the x is equal to, a to the x times the ln of a. So in this case, the a is our 2 here. So that derivative would just be 2 to the x times the natural log of 2. All right, then minus the derivative of sine of x, which we know is cosine x. We've done a few of those here already. Okay, again, there's our derivative function. Let's go ahead and evaluate that for 0. Let's find g prime of 0 would be equal to 2 to the 0 times the natural log of 2 minus cosine of 0. And evaluating that, cleaning things up, 2 to the 0 is just a 1. Any base raised to the 0th power is a 1. So this first term just turns into an ln 2. And then minus cosine of 0. Remember, our cosine function goes like this, which is at a 1 at x equals 0. So that'd just be minus a 1. All right, there's my exact answer for this one. All right, part C and D are similar questions, okay, utilizing those other derivative definitions, those derivative formulas. Why don't you take a couple minutes here, pause the video, try to work through C and D, and then hit play to check your answer. All right, last thing we're going to do is take a look at a few questions that involve relating our derivative rules we've been using to the definition of our derivatives based on limits. And I guarantee you're going to see one AP exam multiple choice question like this, where if you recognize what they're asking, it's a easy point you're going to get done in 30 seconds and move on to. Okay, so for example, evaluate each limit. Okay, we've got the limit as h goes to 0 of sine of x plus h minus sine of x over h. Now what I could do is I could actually evaluate this limit, expand things, cancel some stuff out. Okay, this could be a very long and tricky problem, but the trick here is that recognizing that this is just my definition of a derivative, which was f prime of x is equal to the limit as h goes towards 0 of f of x plus h minus f of x all divided by h. Okay, that's the form we have here. Okay, where in this case our f is just the sine, so this is just the same thing as we could say d over dx of sine of x, which we know is just a cosine of x. All right, so kind of a trick question. This is just applying our definition of a derivative to the sine function, which we know the derivative of, which is just cosine of x. All right, let's take a look at another example. Kind of the same thing here. we've got the limit as h goes to 0 of some functions with an h on top. So it looks like this is using our definition of a derivative. The trick is I don't really have the x's in here. I've got a 1. So it looks like what we're doing is we're evaluating the derivative at a specific point. So first thing I'm going to want to do is rewrite this limit. And I want to think of how can I get this negative 1 out of e to some power? Well, I can rewrite this one as just e to the 0 plus h instead of just e to the h. Okay, minus a 1 is the same thing as e to the 0 all over h. So what this limit is asking us to do is take the derivative with respect to x of e to the x, but we're going to evaluate it for x equals 0. All right? Derivative of e to the x is just e to the x. So we'll just plug in the 0 there. E to the 0 is just a 1, which is why this entire limit is just going to evaluate to a 1. All right, let's take a look at one more example here. And this one we're looking at the limit as x goes towards 2 of ln x minus ln 2 over x minus 2. Okay, here what we're using is we're using that alternative form of the derivative. Okay, f prime of a is equal to the limit as x goes towards a of f of x minus f of 2 divided by x minus a. I suppose this isn't a 2, this is an a in this case. That's our alternative definition. So really what this is this is just a derivative at a point where my f of x is just the ln function, the natural log function. So this is the same thing as the derivative with respect to x of ln x evaluated as x equals 2, which we know is just a 1 over x, where the x is the 2. So that'd just be a 1 over 2, 1/2 for an answer there. All right. There's a few examples of how we can relate our definition of the derivative, okay, to the derivative rules we just learned here. There's also a part C, D, and E. Why don't you take a minute, pause the video, work through those, and then hit play to check your answer again. All right, that's it for 2.3, our lesson on derivatives of sine, cosine, exponential, logarithmic functions. Kind of a lot going on there, a lot of different rules to use, but we're kind of applying them all the same. We're just taking the rule that you're given, throwing it into the different functions, evaluating. Okay, so really all kinds of ties together nicely. All right, that's it for 2.3. Go ahead and give the homework a shot. Make sure you're asking questions if you got them. We're always here to help if you need it.